Welcome to minimize the maximum waiting time at Synchronized Traffic Lights, a LeetCode medium. You are given a cycle length called period, an array lights, where lights I is how many seconds light I stays green, and an array arrival time for each car. At time 0, every light starts green together, and every cycle lasts exactly period seconds. Assign each car to exactly one light. Multiple cars may share a light, and cars do not block each other. Return the smallest possible penalty you can achieve. Picture one cycle as a timeline of length period. The first light's eye seconds are green. The remaining period minus light's eye seconds are red. Then the pattern repeats forever. Because every light starts green at time 0, the lights are synchronized, even though their green lengths can differ. To place a car inside the cycle, compute R equals arrival time modulo period. That remainder tells you where the car lands in the repeating green-red pattern. Here is the waiting rule. For a car with remainder R assigned to light I, if R is less than light's I, the light is still green, so wait is 0. Otherwise, the car is in the red phase, and it must wait until the next green, which takes period minus R seconds. Critical detail. When a car is forced to wait, that wait value depends only on R and period, not on which light you chose. The light only decides whether you get wait 0 or you are stuck with period minus R. After you assign every car, look at all waiting times. The penalty is the maximum among them, the worst wait any car suffers. Your job is to choose assignments that minimize that worst case value. We are not minimizing the sum of weights. We are minimizing the maximum weight. That min-max framing is the whole objective. Example 1. Period 8, lights 2 and 3, arrivals 2, 5, 8, and 11. Remainders are 2, 5, 0, and 3. One optimal plan. Remainder 2 uses the green 3 light and waits 0. Remainder 5 waits 8 minus 5, which is 3. Remainder 0 is green immediately, wait 0. Remainder 3 waits 8 minus 3, which is 5. The maximum is 5, and that is the answer. Now the key insight. To give a car wait 0, you need some light whose green is strictly greater than R. The light with the longest green, call it G, equals max of lights, covers every remainder that any shorter light could cover, plus more. If even G cannot cover a remainder, that is, if R is at least G, then no light can save that car. Smaller lights never help a car. The maximum light cannot save. So after computing G, every car falls into one of two buckets. If R is less than G, the car is coverable. Assign it to the max green light and wait is 0. If R is at least G, the car is forced to wait, and that wait is locked to period minus R, no matter which light you pick. Therefore, the minimum possible penalty is simply the maximum of period minus R over all forced wait cars, or 0 if every car is coverable. No fancy matching is required. Check all 3 examples with this rule. Example 1, G is 3. Forced remainders 5 and 3 give weights 3 and 5, max 5. Example 2, period 10, G is 8. Only remainder 9 is forced, wait 1. Example 3, period 5, G is 2. Forced remainders 2, 3, 4 give weights 3, 2, 1, max 3. Every sample matches. The medium problem collapses to a 1-pass scan. Algorithm recipe. First set G to the maximum value in lights. Initialize answer to 0. For each arrival time t, let R be t modulo period. If R is greater than or equal to G, update answer to the max of itself and period minus R. Finally, return answer. Covered cars never touch the answer because they can always wait 0. In JavaScript, take math max over lights to get G. Loop each arrival t, compute R as t modulo period, and whenever R is at least G, set ANS to math max of ANS and period minus R. Return ANS. Tiny code, because the hard assignment problem reduced to tracking the worst forced wait. Time is O of meters plus N. 1 pass to find max green. 1 pass over arrivals. Space is O of 1. Remember the story. Wait on red is always period minus R. 0 wait needs a green longer than R. The longest green covers every savable car. The answer is the worst forced wait among the rest. That is, minimize the maximum waiting time at synchronized traffic lights.